Now, let me give a definition of a support of a random variable. So, for a given r greater than 0 and x belonging to R p, let an R x, which we call as a neighborhood of x or a ball of radius r centered at x, is given by collection of all those t belonging to R p, such that square root of summation I is equal to 1 to p t I minus x I whole square is less than r. So, this is basically a ball of radius r centered at x. So, if you look at in R 2, it would be like this. So, this is your x, this is your r, and these boundaries are not included because it is strictly less than r. So, this is what your NRx is. We also sometimes call it a neighborhood of radius r centered at x, or a p dimensional ball of radius r centered at x. Now, if x is continuous, then the set S x, which is collection of all those x belonging to R p, such that probability that x takes value in any neighborhood centered at x is positive for every r greater than 0, is called the support of random variable x. So, this is an obvious extension of the similar definition we gave for one dimensional random variables. So, I will say that a point is in support of a random variable if however small neighborhood I take around that point, probability that x takes value in that neighborhood should be positive. Now, let us see this result, which is an analog of similar result in the case of one dimension. So, let x equal to x 1 x 2 p be a p dimensional random vector with distribution function f x. Suppose this distribution function is such that I can get this pth ordered partial derivative everywhere. Suppose this x is everywhere, except possibly on a set D comprising of a finite number of curves in R p. And suppose this whole function turns out integrates out to 1, R p delta x 1 delta x 2 delta x p f x x I d complement x d x. So, leaving those finite number of curves, if I take this function, this integrates out to 1. Then I can say that x is absolutely continuous with its PDF given by this quantity, if x does not belong to D and 0 otherwise. Note that similar result we had in case of one dimension, which was if your distribution function is differentiable everywhere except at possibly finite number of points, and if the derivative of the distribution function integrates out to 1, then I can say that random variable is absolutely continuous with PDF given by the derivative wherever it exists, and at all other points I can take it to be 0. So, this is one of the PDFs. Now, let us look at another important result. So, suppose x is x 1 x 2 x p minus 1 x p. Suppose this is a p dimensional random variable, and suppose its joint distribution function is f x, and its joint PDF. So, this would be PDF is f x. Then the random variable y is equal to x 1 x 2 x p minus 1. So, I have excluded x p, I consider a random vector x 1 x 2 x p minus 1. This is also absolutely continuous, and its PDF would be nothing but obtained by integrating out the joint PDF of x 1 x 2 x p. I integrate out the unwanted variable, the argument of the unwanted variable which was x p in this. So, what it suggests is that if you have an absolutely continuous random variable, and if you are talking about marginal distribution of x 1 x 2 some components of x 1 x 2 x p, you can get the PDF of marginal distribution by integrating out the unwanted variables. The proof is very simple. The joint PDF of y is equal to x 1 x 2 x p minus 1. I know that its distribution function, in the distribution function, if I take the unwanted variable to infinity, I get the marginal distribution function. So, since I have to get the marginal distribution function of x 1 x 2 x p minus 1, I take the argument of x p, random variable x p, to infinity. So, that is what I am doing. But this quantity is same as minus infinity to y 1, minus infinity to y 2, minus infinity to y p minus 1, minus infinity to y p, and the joint PDF, and I limit y p going to infinity was anyway sitting over here. So, I can justify that I can take this limit inside. So, that is what I am doing. So, minus infinity to y 1, minus infinity to y p minus 1, this limit has been taken inside. So, this becomes since y p is going to infinity, this becomes minus infinity to infinity f x t 1 t 2 t p minus 1 t p, and this argument t p, and then d t p minus 1 d t. So, what we have seen? We have seen the distribution function of y 1, y 2, y p minus 1 can be written as indefinite integral of this function. So, this suggests that y 1, y 2, y p minus 1 has to be absolutely continuous, and its PDF would be nothing but this, because this is the function I am integrating out as a definite integral. So, which is same as minus infinity to y 1 minus infinity to y p minus 1 h t 1 t 2 t p minus 1 d t p minus 1 to d t, where y is y 1, y 2, y p minus 1 belongs to R p, where this h t 1 t 2 t p minus 1 was the inner integral, which was basically this quantity minus infinity to infinity f x t 1 t 2 t p minus 1 t p d t. So, this is over here. So, h t 1 h 2 2 h t p minus 1 is nothing but minus infinity to infinity f x t 1 t 2 t p minus 1 t p d t p. So, what it proves? It proves that distribution function of y 1, y 2, y p minus 1 can be written as definite integral of this function. So, that means y 1, y 2, y p minus 1 is absolutely continuous, and its PDF is nothing but h t 1 t 2 t p minus 1, or I am writing down that as h y 1, y 2, y p minus 1, which is same as minus infinity to infinity f x y 1, y 2, y p minus 1 t p d p. So, if you have to get the marginal PDF of an absolutely continuous random variable, you integrate out the arguments of unwanted variables. So, very nice result. So, one can get the marginal distribution marginal PDFs from the joint PDFs. So, this is what this remark says, that marginal distributions of absolutely continuous random variable are absolutely continuous. Moreover, the marginal distribution of absolutely continuous random variable can be obtained by integrating out the arguments of unwanted variables in the joint PDF. So, this is a very useful result. Now, let us talk about the conditional distributions. As I have said, the concept of conditional distributions is very important. For example, let us say if there is a population and you are interested in studying the height and weight of students simultaneously, then sometimes it may be of interest to study the probability distribution of height of all those students whose weight is 70 kg. So, given that weight is 70 kg, what is the probability distribution of height? So, that means you are considering only the probability distribution of a part of a population of students having weight only 70 kg. So, let z is equal to x and y, a p plus q dimensional absolutely continuous random variable with joint distribution function f z, support s z and PD of f z, where x equal to x 1 x 2 x p is a p dimensional absolutely continuous random variable with joint distribution function f x, support s x and PD of f x. Similarly, suppose y is equal to y 1 y 2 y q is a q dimensional random absolutely continuous random variable with joint distribution function f y, support s y and PD of f y. So, that is why this is p dimensional, this is q dimensional, this becomes p plus q dimensional. Let x belonging to S x, which is a support of x, be such that the density at point x is always positive. Then the conditional distribution function of y given x equal to x is defined by f y x given y is equal to x, probability y less than or equal to y given x equal to x. Now, in the discrete case, this probability was well defined if x was in S x, but in absolutely continuous case, I know that if x belonging to S x, then this probability x equal to x is 0. So, I have to slightly modify my definition. So, what I do is I approximate this point x equal to x through a point in a rectangle whose one of the vertices is x, and then I shrink this rectangle in such a way that it sinks to a single point x. So, that is what I am saying. So, given that x is in the rectangle centered at x is in rectangle of the type x 1 minus h 1, x 1, then x 2 minus h 2 to x 2. So, this is the rectangle, and then I take limit h I going to 0. So, that means I shrink this integral this rectangle to a single point. So, that is what I am doing. So, that is how it is defined. So, if this limit exists, I will say that distribution function, this conditional distribution function exists. So, let us look at this is same as limit h I going to 0. The definition of conditional probability of A given B is same as probability of A intersection B. So, x I lying between this to this, probability y less than or equal to y, divided by probability of B, which is probability of this. So, which is probability x I lying between x I minus h I to x I for I is equal to 1 to B. Now, x is absolutely continuous. So, I can get this probability by integrating out the PDF in this region. So, x i's are the first p components. So, x 1 minus h 1 to x 1, x p minus h p to x p, and the remaining q components are to be integrated in minus infinity to y 1, minus infinity to y q, f z, s t. The inner ones are y 1, y 2, y q. So, d t, d s divided by again this. Here I just look at the marginal PDF of x, which is f x s. I integrate it in the range x 1 minus h 1 to x 1, x p minus h p to x p. So, this is what this probability is. So, I go a little bit further. So, what I do is I take this limit. One way, a rough argument or a very loose argument could be you can apply the L'Hopital rule. It is not a very rigorous argument, but one can apply the L'Hopital rule. So, if you look at this is a 0 by 0 case. So, you have to differentiate. When you differentiate, these becomes x I minus h I is over here. This remains. This becomes x I minus h I, and when you go to h I going to 0, this argument over here gets replaced by x, and that is what is happening over here. So, this same as minus infinity to y 1, minus infinity to y q, f z. This all is sinking to x t d t divided by over here f x x. That is what you get. A more rigorous argument can be given by dividing numerator and denominator by h 1 h 2 h p. You can divide it here h 1 h 2 h p, here you can divide h 1 h 2 h p, and then take the limit, and it turns out to be this. One can easily solve it, but I have given you a kind of a loose argument, which is not very rigorous, but correct under certain conditions, and if you take the limit, then you get this. So, these are distribution function of y at the point y when x is fixed at small x. So, I can take this over here, divide it over here, and that is what. So, I can f x x is common, I distribute inside the integral. So, this becomes minus infinity to infinity, minus infinity to y q h x t d t. Note that here x was fixed, small x was fixed. So, this x I have combined with f x f z x t, then minus infinity to y 1, minus infinity to y q, f z x t divided by f x x you get. So, this is what you get h x t, which is nothing but f z x t divided by f x x. T is t 1 t 2 t q belonging to R. So, what it says? The conditional distribution function can be written as definite integral of h x t, which is this function is non-negative. So, it follows that the conditional distribution function of y given x equal to x, where x belonging to x x is such that f x x is positive. So, this is fixed, this small x is fixed, is absolutely continuous. And what is the PDF? PDF of y given x is f z x y divided by f x. So, this if I call this as a conditional PDF is nothing but joint PDF divided by marginal of whatever was given. Given was x was fixed at small x. So, one can easily check that if I integrate this over whole R p, only y component, there is no y over here. So, that means I have to integrate this whole R p. If you integrate this over R, if I integrate this over arguments of y, I get the marginal of x, and marginal of x divided by marginal of x would be 1. So, if I integrate this conditional PDF over arguments of y, because here x is fixed, I get 1, and this is clearly non-negative because it is a ratio of 2 PDFs. So, the definition of conditional distribution function given in B above holds for general random variables. So, I can define the way I define the conditional distribution function here. for any arbitrary random variable, because this definition holds for the discrete also, because in the discrete case through monotonicity of probability measure, this probability would mean nothing but probability x equal to x. So, this definition holds for arbitrary random variables, distribution function at least. So, now we are in a position to give the definition of conditional PDF or conditional distribution. So, let Z is equal to x 1 x 2 x p y 1 y 2 y q be a p plus q dimensional absolutely continuous random variable with joint PDF f z. Let x equal to x 1 x 2 x p, y is equal to y 1 y 2 y q, and let f x be the marginal PDF of f x. Now, let x belonging to S x be such that f x x is positive. So, I am fixing this x 1 x 2 x p. Then the conditional PDF of y given x equal to x is defined by f y given x as joint PDF of x and y given the marginal of whatever was fixed f x x y belonging to R q. Now, this ratio is well defined because I had fixed my small x in such a way such that f x x is positive. So, conditional PDF is nothing but joint PDF divided by marginal of conditioned variable, marginal PDF of conditioned variable.